Last lecture, we spoke about image formation, and now we'll move on to how do you represent an image so you can process it using transformations. So we did leave one question during the last lecture, which is if the visible light spectrum is Vibgyor, goes from violet to red, why do we use an RGB color representation? Hope you all had a chance to think about it, read about it, and figure out the answer. The answer is the human eye is made up of rods and cones. The rods are responsible for detecting the intensity in the world around us, and the cones are responsible for capturing the colors. And it happens that in the human eye there are mainly three kinds of cones, and these cones have specific sensitivities, and the sensitivities of these cones are at specific wavelengths which are represented by S, M, and L on this particular figure. So if you look at where these cones peak at, that happens to be close to red, green, and blue, and that's the reason for representing images as red, green, and blue. In all honesty, the peaking does not happen exactly at red, green, and blue. It actually happens at some off colors in between. But for convenience, we just use R, G, and B. Some interesting facts here. It happens that the M and L wavelengths here are stronger on the X chromosome. So, which means males who have the XY chromosome, females have the XX, are more likely to be colorblind. So also, it's not that all animals have the same three cones. While humans have three cones, night animals have one cone, dogs have two cones, fish and birds have more color sensitivity, and it goes to 4, 5, or in a mantis shrimp, it goes up to 12 different kinds of cones. So nature has abundance of how the colors are perceived. Moving on to how an image is represented. The simplest way to represent an image, which you may have already thought of, is to represent an image as a matrix. So here is a picture of the Charminar, and if you look at one small portion of the image, the clock part, you can clearly see that you can zoom into it and you can probably represent it as a matrix of values, in this case lying between 0 and 1, and obviously you'll have a similar matrix for the rest of the image too. So, but it's very common in practice. While we are talking here about using it with values 0 to 1, in practice people use up to a byte for representing each pixel. So which means every pixel can take a value between 0 and 255 to power 8, and in practice we also normalize these values between 0 and 1, and that's the reason why you see these kinds of values in a representation. And also to keep in mind is that for every color channel you would have one such matrix. So if you had a red, green, blue image, you would have one matrix for each of these channels. What would be the size of this matrix? The size of this matrix would depend on the resolution of the image. So recall again what we spoke about the image sensing component in the last lecture. So depending on what resolution the image sensor captures the image in, that would decide the resolution and hence the size of the matrix. A matrix is not the only way to represent an image. An image can also be represented as a function. Why so? It just helps us have operations on images more effectively if we represent it also as a function, certain operations at least. So in this case, we would talk about this function being going from r square to r, where r square simply corresponds to one particular coordinate location on the image, say I comma j, and that's what we mean by r square. And the range r is the intensity of the image that could assume a value between 0 and 255 or 0 and 1 if you choose to normalize the image. And a digital image is a discrete, a sampled, quantized version of that continuous function that we just spoke about. Why is it a sampled, quantized version? By sampled, we mean that we sample it at that resolution. Originally, the function can be continuous, which is like the real world in which the image was captured. Then we sample the real world at some particular pixel values on some grid with respect to a point of reference. And that is what we call as a sampled discrete version of the original continuous function. Why quantized? Because we are saying that the intensity can be represented only as values between 0 and 255 and also in the same steps. You cannot have a value 0.5 for instance, at least in this particular example. Obviously you can change it if you like in a particular capture setting, but when we talk about using a byte for representing a pixel, you can only have 0, 1, 2, so on, so forth till 255. You cannot have a 0.5. So you've actually discretized or you've quantized the intensity value that you have in the image. So let's talk about transforming images when we look at them as functions. So here is an example transformation. So you have a face and we seem to have lightened the face in some way. What do you think is the transformation here? Can you guess? In case you have not, the transformation here is if your input image was I and your output image was I hat, you can say that I hat is I of xy plus 20. 20 is just a number. If you want it to be more lighter, you would say plus 30 or plus 40. Again, here we are assuming that the values lie between 0 and 255. One more example. Let's say this is the next example where on the left you have a source image, on the right you have a target image. What do you think is the transformation? The transformation is y hat of xy would be I of minus x comma y. The image is reflected around the vertical axis. The y-axis is fixed and then you rotate, you flip the x-axis values. If you notice here, both of these examples, the transformations happen point-wise or pixel-wise, right? In both these cases, we have defined the transformation at a pixel level. Is that the only way you can perform a transformation? Not necessarily. Very broadly speaking, we have three different kinds of operations that you can perform on an image. You have point operations. Point operations are what we've just spoken about, where a pixel at the output depends only on that particular pixel, the same coordinate location in the input. That would be a point operation. A local operation is where a pixel at the output depends on an entire region or neighborhood around that coordinate in the input image. And a global operation is one in which the value that a pixel assumes in the output image depends on the entire input, image. In terms of complexity, for a point operation, the complexity per pixel would just be a constant. For a local operation, the complexity per pixel would be p square, assuming a p cross p neighborhood, a local neighborhood around the coordinate that you're considering for that operation. And in case of global operations, obviously the complexity per pixel will be n square, where the image is n cross n. Let's see a couple of more point operations and then we'll see local and global. So here is a very popular point operation that you may have used on your smartphone camera or Adobe Photoshop or any other task, image editing task that you took on. It's an image enhancement task and we want to reverse the contrast. So by reversing the contrast, we want the black to become white and a dark gray to become light gray, so on and so forth. What do you think? How do you implement this operation? Okay, in case you have not worked it out yet, the operation would be at a particular pixel, it's a point operation. So at a particular pixel m0, your output will be Imax minus the original pixel at that location plus Imin. You're flipping it. So if you had a value, say 240, which is close to white, generally white is 255 and 0 is black. If you had a value 240, now that's going to become 15 because Imax in our case is 255 and Imin is 0. When Imin is 0, Imin obviously does not matter, but this formula is assuming a more general setting where Imin could be some other value that you have in practice. Moving on, let's take one more example of image enhancement again, but this time we're going to talk about stretching the contrast. Okay. When we stretch the contrast, you're taking a set of values and you're stretching it to use the entire set of values that each pixel can occupy. Okay, so you can see here, this is again a very common operation that you may have used if you edited images. What do you think is the operation here? Okay, this is slightly more complicated than the previous one. In case you already don't have the answer, remember, let's first find out the ratio. So you have a typical Imax minus Imin, which is 255 minus 0, by max of I in this image minus min of I in this image. Let's assume hypothetically that this image on the left had its max value to be 200 and its min value to be 100. Okay. If that's the case, this entire ratio here that you see is going to become 2.55. This is 255 minus 0 divided by 100, 200 minus 100, which will be 2.55. So you're simply saying that I'm going to take the original pixel, whatever is, let's assume for the moment that the original pixel had a value, say 150. Okay. So if this had a value 150, so you're subtracting the minimum, so which means now you have a value, the minimum is 100. So you're going to have 50 into 2.55 plus Imin for us, which is 0, which roughly comes to 128. Right? So that's 50% of the overall output. So what was 150, which was in the middle of the spectrum in the range of values that we had for this input image, now becomes 128, which becomes the middle of the spectrum for the entire set of values between 0 and 255. You're simply trying to stretch the contrast that you have to use all the values that you have between 0 and 255, which means what would have gone from dark gray to light gray now goes from black to white. That's how you increase a contrast. So this is called linear contrast stretching, a simple operation again. But in practice, we do something more complicated. So we do what is known as histogram equalization. You may have again heard about it, perhaps used it in certain settings. If you heard about it, read about it, and that's going to be your homework for this particular lecture. Okay, so let's ask the question, do point operations satisfy all the requirements we have of operating on images? Let's take one particular example. So we know that a single point's intensity is influenced by multiple factors. We talked about it the last time, and it may not tell us everything. So because it's influenced by the light source strength, direction, surface geometry, sensor capture, image representation, so on. So it may not be fully informative. So let's take an example to show this. So let's assume we give you a camera and you have a still scene, no movement. How do you reduce noise using point operations? The noise could be caused by some dust blowing in the scene, could be caused by a speck of dust on the lens of your camera, or by any other reason for that matter. There could be a damage on one of the sensors. Noise could be at various levels. How would you reduce noise using only point operations? The answer, you have to take many images and average them. Because it's a still scene, you can keep taking images and hope that the noise gets averaged out across all of your images that you took. And you take the average of all of your images. It's a bunch of matrices. You can simply take an element-wise average of all of those matrices, and that can help you mitigate the issue of noise to some extent. But clearly, that's a stretch. You don't get multiple images for every scene all the time, and you don't get a still scene that's absolutely still all the time too. There's always some motion, and so this may not be a method that works very well in practice. So to do this, we have to graduate from point operations to local operations. So let's see what a local operation means. As we already said, a pixel value at output depends on an entire neighborhood of pixels in the input around that coordinate, okay, whichever coordinate we want to evaluate the output at. So here is a very simple example to understand what a local operation is. A standard example is what is known as the moving average. So here you have your original input image I. As you can see, the input image I is simply a white box placed on a dark gray background, or in this case a black background, because you can see zeros as the values. So we assume that that means a black background. So the image has a particular resolution. In this particular case, it is a 10 cross 10 image, and the white box is located at a particular region. But the problem for us is we are going to assume that this black pixel in the middle here and this white pixel here are noise pixels that came in inadvertently. So how do you remove them? So the way we're going to remove them is to consider a moving average. So you take a 3 cross 3 window, need not be 3 cross 3 all the time, it could be a different size. But for the moment, we're going to take a 3 cross 3 and simply take the average of the pixels in that particular region. So the average here turns out to be 0. So you fill it at the center location of that box. Moving on, you now move the 3 cross 3 box to the next location. You again take an average. Now the sum turns out to be 90, 90 by 9, 10. Similarly, move the box, slide the box still further, and once again take the average of all pixels in the box in the input, and that gives you one value in the output. Clearly you can see that this is a local operation. The output pixel depends on a local neighborhood around the same coordinate location in the input image. And you can continue this process, and you finally will end up creating the entire image looking somewhat like this. So you can see now, you may have to squint your eye to see this. You can see now that the seemingly noise pixels here and here in the input have been smoothened out because of the values of the neighbors, and the output looks much smoother. Here is a low resolution image, so it looks a bit blocky, but if you had a higher resolution, it would look much smoother to your eyes. So what is the operation that we did? Let's try to write out what operation we did. So we said here that I hat at a particular location, say xy, is going to be, you're going to take a neighborhood, so which means you're going to take the same location in your input image and say you're going to go from say x minus some window k to x plus some window k. Similarly, you're going to go from some y minus k to y plus k, and let's call this say I, let's call this say j. You're going to take the values of all those pixels in the input image, and obviously you're going to average all of them. So you're going to multiply this entire value by 1 by because the neighborhood goes from x minus k to x plus k. There are totally 2k plus 1 pixels there, right? So you're going to have 2k plus 1 square, because for x you'll have 2k plus 1 pixels, for y you'll have 2k plus 1 pixels, and then you just so the total number of pixels is going to be one across the other. And in this particular examples that we saw, k was 1 for us. We went from x minus 1 to x plus 1. So if you took a particular location on the output, you took the corresponding location of the input, and then one to the left and one to the right, right? So from x minus 1 to x plus 1, y minus 1 to y plus 1, and that creates a 3 cross 3 matrix for you, and that's what we're going to finally normalize it by. That becomes the operation that you have for your moving average. So this is an example of a local operation. Moving to the last kind of an operation called a global operation, as we already mentioned, in this case, the value at the output pixel depends on the entire input image. Can you think of examples? In case you've already not figured out, a strong example of something like this is what is known as a Fourier transform. We'll see this in a slightly later lecture, but there are other operations too that can be global depending on different applications. We'll see more of this a bit later, and we'll specifically talk about Fourier transform a bit later. That's about this lecture. So your readings are going to be chapter 3.1 of Seliski's book. And also, as we mentioned, think about the question and read about histogram equalization and try to find out how it works and what's the expression you would write out to make it work.